Good afternoon, everyone, and welcome to our session, Best Practices for Serverless Developers. Who here is a serverless developer?
Yay.
Nice. We're going to get even more after today. So my name is Gunnar. I'm a developer advocate at AWS, and I've been working with serverless technologies for quite a few years by now. And I'm very excited to be able to be here and share some insights with you today. But before we dive in, I want to introduce my co-speaker. He's known as the smartest guy in serverless, Jan.
Thanks, Gunnar, and hi, everyone. My name is Yan Cui. I'm an AWS serverless hero and independent consultant. And like Gunnar, I've been using serverless and AWS for quite a number of years now, going all the way back to 2016. So yeah, really excited to share what we've learned the last couple of years with you guys, so that you can catch up and do what we do as well.
All right, thanks, Jan. And in this session, we're going to cover a range of topics from serverless evolution to practical implementation strategies. And we want to aim to give you actionable insights that you can apply on your own serverless project. So let's get started. This is what we'll cover today. And serverless best practices, well, that's a vast topic. So we've organized it into 5 key areas. And I want to set expectations. We'll be moving fast because we have a lot of things to cover. So don't worry about catching everything. The slides and additional resources will be available afterwards as well. So let's dive in. The evolution of serverless, it has really been the story of the cloud, because the cloud was born serverless with the launch of Amazon S3 and Amazon SQS back in 2006. And that was even before you could rent a virtual machine with Amazon EC2. And then we kept adding services that were just pay as you go, so no infrastructure for you to manage. But it was really in 2014 when serverless really came alive, and that was revolutionary with the launch of AWS Lambda. You just upload your code to the cloud, and we will then securely run it for you, highly available, and at scale. Then we had ECS at the same year, launched as well, and then shortly after, we launched Fargate as well. And Fargate allows you to run containers in a serverless way. And now there's a huge amount of different serverless services that you can use across compute, storage, workflows, integrations, databases, analytics, and more. Pretty much all of AWS has services that are serverless today. And there's a huge number of partners who offer serverless solutions as well, so you can pick and choose the best tool for the job. And customer adoption of serverless, well, that's everywhere today. Every industry, everyone from startups through enterprises, government, and everything in between, serverless is transforming how customers build today.
And as customers, we love serverless because it allows us to iterate quickly and trial out ideas and bring them in front of our customers fast, quickly as well, which in this really competitive market that we're in today, this is a really, really important business advantage that we have. And then the great thing about using serverless and using fully managed services is that they're always getting better, faster, and more cost efficient. Recently, AWS announced that there's a 94% improvement on latency to EventBridge, and this is not just a one-off instance either. Over the last 5 years, EventBridge has gradually improved the latency for their services, so the end-to-end latency for my event-driven architectures has gotten better over time without me having to do anything. Now, for me, that's the best kind of optimization where somebody else is doing all the hard work, so I don't have to. And nowadays, if you imagine you've got some kind of food delivery service, and you have to send the real-time updates about your customer's order to the user. Imagine the front end have to talk to a number of services, and they have to say, get order information, place orders, and so on. This is done synchronously via API calls, but we also have lots of background services that want to send updates to the front end, to the user in real time. So we know we can do this with polling, but polling is wasteful, it's expensive, it's a lot of unnecessary API calls to the back end, and it's also a bad user experience because you have to wait for the next polling cycle to get a message delivered to the front end. So instead, what we can do is have the backend processes send those updates asynchronously via EventBridge bus, and the EventBridge is going to take those messages and deliver that to an AppSync API, for example. So we can then from there send the real-time update to the front end via WebSocket using AppSync subscriptions. Nowadays, EventBridge can deliver events to GraphQL to AppSync APIs directly without you having to have a Lambda function in between just so they can speak GraphQL, because EventBridge can now do that by making a GraphQL mutation request. And AppSync allows you to build serverless WebSockets with either the AppSync subscriptions, which is basically GraphQL over WebSocket, or if you want something that's more raw WebSocket, that's more bi-directional, you can then also use the new AppSync Events API as well. And that's great, because now you can build real-time applications without having to worry about scaling, managing, provisioning infrastructure yourself.
So the next topic we want to cover is serviceful serverless, using configuration instead of using code, and using managed services and features wherever that is possible. So serviceful means that as an application becomes increasingly serverless, they rely more on external services to provide these building blocks of the system. And this is a concept that's been advocated by experts like Patrick Debois of DevOps fame and Ben Kehoe, another serverless hero. And instead of having your application in a large compute-based code base, you migrate components into discrete managed services. So you use services like API Gateway for auth, caching, and routing, and you choose the best service for message, data, transport, and storage. And you take advantage of the native capabilities, and then you let us at AWS handle all of that undifferentiated heavy lifting. So when applications become more distributed, another thing to think about is how you use orchestration and choreography as communication methods. And instead of writing your own code, you then manage this with the help of configuration. In orchestration, you have a central coordinator that manages the interaction and the order in which different services are used. And with choreography, there's less central control. Events flow between these services, and then they react on those. Many applications use both choreography and orchestration today for different use cases. And you can think of orchestration as workflows and choreography as events. So with step functions, that's an example of a workflow orchestrator, doing that central coordination and ordering to manage a workflow. And then EventBridge, that is a great choreographer. When you don't need strict ordering and workflows, and you just need events to flow seamlessly without having any centralized control.
And oftentimes, you don't even have to write Lambda functions just so that you can take data from one place to another. So if, say, for example, you want to capture some data change event in DynamoDB and use that to trigger something else to happen in your system, maybe to send it to an event bus or to trigger some third-party API call, you can also just do that nowadays by having EventBridge pipes between the DynamoDB stream and your target as well. So that way, you don't have to write any Lambda functions yourself, and the EventBridge can handle all the retries as well as authentication for you. And because it's a fully managed service, so now you don't have to manage and provision and deal with any infrastructure for your application. And the same thing goes to step functions. So instead of having all those Lambda functions in your state machine just so that they can call some other AWS services with the AWS SDK, you can actually just let step functions do it for you by having step functions talk to other AWS services directly using the SDK integration as well. So you have the same business logic, but minus all the overhead of having to write, deploy, and manage Lambda functions, and also paying for the execution as well. And obviously, you can also mix and match these two different approaches. I mean, sometimes having a Lambda function is just easier, and it's also what you're familiar with as well. And so you can absolutely do that. That's absolutely fine as well.
And if you didn't know, there are actually two flavors of step functions. There's the standard workflows. They can run for up to a year, and they are asynchronous. And then we have the express workflows, which are fast, and they're built for high throughput. They can run for a maximum of 5 minutes, and they can also be synchronous. So the pricing is different. Standard workflows are priced per state transition. And then express workflows, they are priced by the number of executions and also the memory consumption. And so express workflows, they can be significantly cheaper. In this example, 1 million standard workflow executions would cost $420, but using express workflows instead, that's just $12.77. It's also half a second faster to run per execution, so it is a performance boost to use express workflows in this case. So take a look at your existing state machines and see where you can potentially save some money, and consider starting using express workflows first. An even better story is how you can use these two together. So you can nest express workflows into your standard workflows. Long-running standard workflows that then support callbacks, and then nest the express workflow for speed and high scale with return to the parent standard workflow when it's complete. A great way to get best of both worlds, which I think is great for budget as well. So, there is often use cases where you do need to run custom code, and I'm suggesting to not use Lambda when you can, but running serverless functions or containers can have some amazing capabilities as a service, and they are worth both understanding and exploring. So starting with Lambda, which is an event-driven execution model. You have something that causes an invoke, you have a Lambda function with your code, and you have the thing that your Lambda function does. And today there are over 140 different services that can invoke a Lambda function on your behalf. And there are 3 ways that they do that. You have the synchronous, which is request response, usually behind an API. Asynchronously, where you don't wait for a response from the function code. You hand off the event to Lambda, and then Lambda just handles the rest for you. Or stream, or poll-based model. It's also often called event source mappings. That runs a Lambda managed poller that reads items from an event source. That could be SQS, Kinesis, or Kafka. And memory, it is the main configuration lever when it comes to Lambda performance tuning. So you configure memory, you then also get proportional CPU and network throughput. Lambda allows memory configuration from 128 megabytes up to 10 gigabytes. More memory equals more CPU. Now, in this example, it's not entirely accurate because the CPU isn't a straight line, there's a stepping action to it, but it shows that as you increase memory, you get more CPU. And at 10 gigabytes, you will get up to 6 cores of CPU. But in order to take advantage of this power, your code has to support the ability to run across several cores. Single core performance, that tops out at around 1.8 gigabytes of memory. So if your code isn't multi-threaded and you're scaling memory only for CPU performance, you won't really see any benefit beyond 1.8 gigabytes. And you will basically just be paying a premium for the privilege. We'll get back to how you can optimize function memory in a bit. The next thing to talk about is the Lambda execution environment lifecycle. So I'm going to talk about cold starts. And I think more has been written about cold starts than any other AWS topic. How many articles have you written, John?
Somewhere between 5 and 10.
Yeah, probably 10. So let's talk about cold starts. This happens when Lambda needs to create a new execution environment for your code. And it can occur when you take actions like scaling up or updating code, or when we at AWS need to refresh environments or rebalance across availability zones. So here's the important part. Cold starts affect less than 1% of all production function invocations. For most workloads that have consistent traffic, cold start isn't a major concern. But if you're running synchronous workloads like APIs, that 1%, it might matter a lot to you. So we're going to cover some strategies for how to help with that. And since Lambda is a managed service, we occasionally need to refresh environments for patching or to make sure that it's highly available. And that's part of the Lambda magic, the things you don't have to care about, but that can also actually trigger cold starts. So let's look at where cold starts happen in the function lifecycle. First, we need to create a new execution environment, and we find a host for your code. Then we download your code or container image. We start the runtime, we run your function's pre-handler code, and finally we execute your first invoke. After that, your function is warm and it's ready for subsequent events. In the managed runtime world, there's a clear separation of responsibilities. Everything up to the runtime initialization, that's on us, AWS, and we've spent years trying to optimize this. We're shaving off millisecond by millisecond, even nanoseconds, to make it faster and faster for you. The Lambda lifecycle explains the cost model. For managed runtimes, you generally pay only per invoke. You pay per millisecond based on the memory size and the duration. And you only pay for init time with container images, OS custom runtimes, or when the init exceeds 10 seconds. So this is cost effective when there is a gap between work to do.
So here are some best practices for reducing the initialization time for your Lambda functions. The single most important thing to consider here is that don't include any dependencies that you're not going to need, and to use techniques like bundling and minification to reduce the size of your Lambda deployment artifact. Generally speaking, every 10 megabytes you add to your deployment artifact is going to add about 100 milliseconds to your Lambda cold start time. And also, if you have some dependencies that are not used in every single execution path, then consider lazy loading them, so only load them when you actually need them. Another thing to take advantage of is the fact that Lambda functions reuses the execution environment that's been created. So if you have to connect to, say, RDS, then you create a connection during cold start and then keep the connections alive so that on subsequent invocations on the same execution environment, you can reuse those connections as opposed to having to create a new connection again. So this is going to be a big performance improvement for your functions. And similarly, if you need to fetch parameters from SSM parameter store or secrets from secrets manager, also do them during cold start and then cache them so that on subsequent invocations, you don't have to go back to those services to fetch your parameters and secrets again.
So, something that we released to help with this is SnapStart. We released it a few years ago for Java, and it's optimizing the Lambda function lifecycle. It runs the full init of your code ahead of time, and then it takes a snapshot or a point-in-time image of that running execution environment. This snapshot is then made available for future Lambda invocations. So with SnapStart, every new invoke starts from a pre-initialized environment. And this is particularly beneficial for Java functions, starting a JVM, or .NET functions doing tiered compilation, or maybe you have Python functions loading heavy libraries. So SnapStart works with no code changes for you. You just toggle a configuration setting. You'll get much faster initialization times. Remember, though, that you have to point to a specific function version. You can't use the latest for SnapStart to work. And Lambda handles one request at a time, regardless of invocation model or what's in front of it. As more requests come in while the first environment is busy, Lambda then spins up a new environment, each one causing a cold start before processing that event. And once the first environment becomes free, Lambda will reuse it for new invocations to avoid cold starts. And we keep warm environments available for this purpose, but if all environments are busy, Lambda will then have to scale automatically with a new environment. And you can then count the concurrency, which is equal to the number of running execution environments. And you can view this concurrency using the CloudWatch metrics for all or for your individual functions. And concurrency, it relates directly to transactions per seconds, or TPS. And this becomes crucial with downstream services like databases or APIs that might have connection limits. So your TPS is determined by your concurrency and function duration. With 10 invocations taking 1 second each, you have 10 TPS. If functions takes half as long, you would get 20 TPS with the same concurrency of 10. And this matters when we're dealing with those downstream services. It might be that you have services throttling at 15 TPS. We then need to consider our concurrency limits in Lambda. And then we have reserved concurrency, which lets you set a limit on a function's concurrency. It helps protect these downstream services from being overwhelmed. It can also act as an off switch when experiencing downstream issues. And provision concurrency, that means that we pre-warm environments for your functions. And with provision concurrency set to 10, we will then run all these inits in advance. Events hit these warm environments without having any cold starts. If an 11th request arrives while our workers are busy, it will then use an on-demand invocation, which will face a cold start again. And you can keep eye on the CloudWatch metrics to avoid over-provisioning. And just like with SnapStart, you have to use a specific function version. You can't use latest for this. Two important concurrency quotas. The account concurrency quota, maximum concurrent executions across all functions within a region. It defaults to 1,000, but it can be raised. And our improved scaling model lets every function scale up to 1,000 execution environments every 10 seconds, making Lambda the fastest way to get massive compute power at AWS today.
And let's talk about scaling and some best practices around the synchronous invocations where you got, say, a Lambda function behind API gateway where the customer or the caller is going to have to wait for your function to complete. Lambda is obviously a very, very scalable service, but you still need to make sure that your system can actually handle the expected load. And so you want to make sure you've got load testing in place to catch any problems, any scalability bottlenecks you may have in your system. Maybe Lambda is fine, but maybe you got a problem with some downstream services you're using. So you want to make sure that you've got your throughput quotas also set up across all the different services you use as well. And also, you want to make sure that your timeouts are aligned across the board because API Gateway has a maximum integration timeout of just 29 seconds, so there's no point setting a Lambda timeout to be more than that. Having said that, it's also worth pointing out that nowadays you can raise that 29 seconds integration timeout with API Gateway if you have a regional or private REST API. Another thing to consider is that for synchronous invocations, the client is going to be responsible for the retries. And when you do have those retries, you want to make sure that you protect your system from retry storms. So you want to make sure you have exponential backoff with a little bit of jitter so that you don't have retries hitting your system all at the same time. And finally, you want to think about item potency, because when your system can be retried, you are going to deal with occasionally having to process duplicated events. So make sure that you handle this gracefully so you don't have a situation where you charge my credit card twice, which would be really bad for you as a service. When it comes to processing stream events from Kafka and Kinesis, you also want to use filters, so you only process data that you actually want. And because the Lambda is going to pull records continuously in the order in which they are received, so you want to, and those ordering is based on the partition or shard, so you want to make sure that your shard and partition ID is going to help you distribute the events somewhat evenly across the different shards, so you don't have hotspots. And because ordering is guaranteed, and you want to make sure that when you do have a poison message, it can stop all processing on that particular shard, and therefore, you want to think carefully about how you handle errors and only deal with things that you can actually safely retry and use Lambdas on failure destination to catch any poison messages. In terms of performance, to help you improve your performance, make sure that your function has sufficient amount of memory and also use larger batch sizes to help you increase your overall throughput. And because Lambda auto-scales based on the number of shards and partitions you have, so adding more shards is also going to help you improve performance and throughput as well. And for Kinesis, you can also increase your throughput, overall throughput, by using the parallelization factor and enhanced fan-out so that you can have more concurrent Lambda executions to handle the data in a single shard. And also, don't forget, monitoring is your friend. So when you are running processing events from Kinesis and Kafka, have alerts and metrics around things like the iterator age as well as the consumer lag, which tells you when your functions start to fall behind.
So let's talk about our other serverless compute option, containers. It is a popular approach. You build your container image with everything you need, you test it locally, then you push it to the cloud to run. And for serverless containers, we have two key components. First, ECS. That's our fully managed control plane. You run individual containers as tasks for short-lived operations, or you group them into services for long-running applications with health management and availability zone awareness. Second, we have Fargate, our fully managed data plane. While you can use EC2 with ECS, Fargate gives you that truly serverless option. We manage all of that underlying instances for you. And Fargate works differently from Lambda. It's more traditional port and socket-based application model rather than the event-driven one. Your container runs whatever you need it to do. And for routing traffic, you just add a load balancer in front of your service. And we will then handle the infrastructure side. We manage instances, scaling, patching the underlying host. And you take on more responsibility compared to running things on Lambda because you have to manage your code, you have to manage the runtime, the libraries in the container, plus also handling load balancing and networking. And you can also control container scaling using auto-scaling with the help of CloudWatch, for instance. So compared to Lambda, the pricing model is pay for what you provision rather than Lambda's pay for what you use in milliseconds. So your container starts and you are charged per second based on the CPU and memory that you configure. But this means it could be more efficient to run when you have high concurrency. Lambda has single concurrency, like we talked about. But you can use multi-concurrency with Fargate and potentially get a lower per request cost.
Yeah, a very common question I get from clients is how do I choose between these two services? And there's obviously quite a lot of different things to consider. I'm not going to go through everything here, but the main thing to consider is that with Lambda, it manages more for you, so you can better focus on the things that differentiates your business from your competitors, so it allows you to iterate faster. That is, so long as you're happy to live within Lambda's limits, like the 15 minutes execution time, or the fact that you can only allocate up to 10 gigabytes of memory to your functions, whereas with Fargate, you can pretty much do whatever you want inside a container, and you can use all these existing container tools that you may be familiar with already. And you can also have a bigger container instances that can have a lot more memory, have different networking modes, but also importantly, you can run for much longer than 15 minutes at a time as well. So the TLDR is that Fargate is the more flexible option, and it's good for things that are long-running, things that are stable, has a high volume, and maybe have a high resource requirement. And the Lambda is a simpler option, and it's good for pretty much everything else. And of course, you don't have to just stick with one. You can always use both in the same application. Say if you want to do some quick processing, then use a Lambda function. But if you do something that's more resource intensive or have to be long running, like transcoding a feature length video, then use a Fargate instance instead. Services like EventBridge, step functions, and many others can integrate seamlessly with both. So you can always mix and match and choose the right tool for the job.
So let's dive into what it takes to make a serverless service truly production ready. We'll cover a few different areas: resilience, observability, security, and governance. These are all essential elements when it comes to transforming that basic serverless application into something that's robust and enterprise grade. So let's start with a basic serverless setup. We have an SQS queue. It's triggering some Lambda function that then writes to an S3 bucket. This looks simple, right? But is this a production-ready service? Not quite. So we want to explore what it takes to elevate this very simple service into something that can be reliably handled real-world demands and challenges. And to make this service truly production-ready, we need to focus on these key areas: resilience, observability, security, governance, and then the Lambda best practices. Each of these play a crucial role in creating a robust, reliable, and efficient serverless architecture. So this quote from Dr. Werner Vogels, you've probably all seen it. He's the CTO of Amazon. It's a fundamental principle in how we build in the cloud today. It reminds us that in distributed systems, failures are inevitable. Instead of trying to prevent all failures, we need to design our system to be resilient and to gracefully handle these failures when they actually occur. And this mindset is crucial as we build production-ready serverless services. So looking at our simple service again, let's consider what can go wrong. SQS will retry failed Lambda invocations, but what if there's a bug in the code or we can't reach S3 for some reason? Messages might get stuck in SQS, retrying over and over until they expire and then they are lost, or they could fail in batches. Either way, it's not a great experience having this happen, so we need to have a better way to handle these types of failures. So this is why we add a dead letter queue, or DLQ. So when our Lambda function fails to process messages, instead of losing them forever, they get redirected to the DLQ. This gives us a chance to then investigate what went wrong and potentially retry these failed operations. This is our first step into making the service more resilient. So let's dive into some of the best practices for SQS and dead letter queue setup. First, we should use a batch size of 10 items. This increases throughput and efficiency. Set the queue's visibility timeout to at least 6 times your function's timeout. This allows Lambda to retry if your function is throttled while processing a previous batch and preventing duplicate processing. And configure the max receive count in your retry policy to at least 5. This helps avoid sending messages to the DLQ due to temporary issues, like throttling, for instance. And finally, set a long message retention period for your dead letter queues. This gives you time to investigate and potentially also reprocess these failed messages. And these settings can help create a more resilient system that can then handle these types of temporary failures. And it gives you time to address these issues.
Yeah, but what's funny is that most people don't actually know what to do once they have captured some messages in the DLQ. I mean, how do you then go about reprocessing those failed messages? And one way to do this is to have a cron job that runs, say, once a day, and then basically redrive those messages from the DLQ back to the main queue so that you can process them again. And this is the automated way of doing things. However, this is good for retryable errors, things like throttling errors and things like that. But there's also risks that you can get stuck in an infinite loop where things keep going back to the DLQ, going back to the main queue, and back to the DLQ again. So you want to be conscious of the errors that you handle so that you only you only let the messages that can be retried go into the DLQ in the first place. Also, to avoid the data loss, make sure that your DLQ's retention period is longer than the frequency of your cron job so that you always get a chance to pick up those messages in the DLQ and reprocess them. And also, you've got to think about idempotency as well. Sorry, took too long to get the idempotency because when you process things again and again, you're going to have to deal with them again. So that, again, you don't want to charge my credit card twice because you're going to get a very angry phone call from me.
It is a business idea, though, charging your card twice. So let's look at how we handle these failed messages. We can implement a redrive mechanism. Basically an API call that moves messages from our dead letter queue back to the main queue. And we typically want to do this once a day, like Jan said, giving us time to fix any issues before retrying. But we need to be smart about how we handle these retries to avoid creating that infinite loop of failure. When handling SQS batches in Lambda, there are 2 key principles to remember. First, implement retry with backoff. Your client should retry failed operations, but use exponential backoff to avoid overwhelming the system. And this prevents that thundering herd issue where too many retries happen at once. And second, we've talked about it multiple times, implement idempotency. This means designing your function to handle repeated messages gracefully. And these practices are crucial for building a resilient application. Your code needs to be aware and to properly handle these scenarios to ensure that we have reliable processing even when things go wrong. So let me show you how to implement this in code. Notice 2 key things here. First, in our import statements, we're being selective, only importing exactly what we need, which helps with cold start times. Second, we're setting up our processor to handle batches with observability and partial failures built in. And this is a pattern that gives us both performance and resilience. And here we're using a hexagonal architecture pattern. This separates our Lambda handler from our business logic. It's making the code more maintainable and also easier to test. And the handler's only job is to receive events and then pass them to our business logic layer. This clean separation of concerns is a key best practice in serverless application design. So let's look at how we handle retries and timeouts. First, notice we're keeping our imports minimal. Once again, this helps with cold starts performance. And we're also setting up our global initializations here, which is more efficient than recreating these configurations for each invocation. And the key point here is the importance of changing the AWS SDK defaults to better match your application's needs. The default retry settings might not be optimal for your specific use case, so it's important that you configure these deliberately for your application.
And of course, we also want to have a good observability as well, so that we can ask questions about the running of our application and be able to infer its internal state from its external output, things like its logs, metrics, traces, and so on and so forth. In terms of logging, you want to make sure that you're doing structured logging with JSON and next slide. Yep, you want to do structured logging with JSON, and also you want to include some correlation IDs in your logs so that you can easily, find related logs messages for a particular issue. So you want to say find logs by customer ID or tenant ID and so on. Of course, cost management is also a big thing when it comes to observability, and to help you reduce the cost for CloudWatch logs, you also want to make sure that you set the default log level to info in production so that you don't collect all those millions and millions of debug log messages where they don't create a lot of value. But you also don't want to be in a situation where you have no debug logs in production, so that when there is an issue, you don't have anything that can help you figure out what the problem is. So what you do in that case is you set a sampling to sample debug logs from, say, 10% of your Lambda function invocations, so that hopefully you have enough logs to cover every single code path in your system. And lastly, you want to set the retention policy for CloudWatch logs to something more reasonable, like 14 days, because the default retention is to never delete any data, which means you're going to pay more and more over time for the storage of your functions, for your logs. Here are a number of useful metrics that you want to keep an eye out, and also set the alarms against for SQS and for Lambda. And of course, don't forget to add any custom metrics that are specific for your services, KPIs. You can do that with CloudWatch EMF as well. And to help you identify performance issues, there's also X-ray, which gives you some really useful insights, things like how long it took Lambda to cold start, the initialization time, and how long it took your function to talk to different AWS services as well through the AWS SDK. And you can also use CloudWatch dashboards to help you visualize and watch out the trends in your metrics. And you should have different types of dashboards. You want to have the high-level dashboard that shows you at a glance how well the system is running. Is it running okay? Is it having problems? But maybe not so much detail that it just clusters things everywhere. So you can have this high-level dashboard displayed in monitors around the office so people can see at a glance what's happening. But then you also want low-level dashboards that's going to allow you to deep dive and figure out why the system is not working, what the problem is. And to also help you instrument your code, you can use the Lambda Power Tools to help you do things like recording, doing structured logging, also recording custom metrics with EMF, but also to then augment your X-ray traces as well. But you can't just think about your Lambda function handler. You also have to instrument all of your shared business logic layer, including any shared libraries that are used by different services and Lambda functions. You have to instrument all of them. So yes, it is a lot of work, and that's why personally I prefer to use Lumigo instead, because they have a really good auto instrumentation, and out of the box they give you most of what you need for debugging, things like the Lambda invocation event, return value, environment variables, as well as the request and responsibility for any HTTP request you make to other services. So you can get most of what you need out of the box without having to manually instrument your application. And another pattern that I've seen more and more now is companies that start to use ephemeral environments by getting their infrastructure as code, investing into your infrastructure as code early and getting it right so that you can easily bring up entire copies of your application. So that ideally, you can do that in the same AWS account, so developers can have different environments to work with to do their work. And you can also do the same thing and create a temporary environment for your application for every feature development. And when you're done, you can then just tear down this environment from your AWS account. You can even go a step further by having a temporary environment for every CI/CD pipeline run, so that when you're running those tests in the CI/CD pipeline, you're not going to pollute your shared environments like dev, test, and staging. And all your test data is going to go to these temporary environments that gets brought up during the CI/CD run and then tear down afterwards. And a very interesting thing here is that once you have this ability to be able to easily stand up copies of your application, now you pave the way towards a cell-based architecture where you can create different copies of your application for different tenants so that you can limit the blast radius of individual tenants. And this is a really, really powerful architectural pattern and something that's used very heavily inside the AWS services that we all use every single day.
So let's talk about security in our serverless application. We operate with a shared responsibility model where we handle security of the cloud, the infrastructure, network controls, the service operations, and you're responsible for security in the cloud, your application code, data handling, and so on. There's 5 essential security practices for your serverless applications. First, never log PII, personal identifiable information. This is crucial. Second, configure your security settings through infrastructure as code. This ensures consistency and makes security auditable. Third, enable encryption both in transit and at rest. Fourth, make sure to block public access to private resources. This might seem obvious, but it's often overlooked. And finally, implement auditing for all access to customer data. You need to know who accessed what and when. So remember where we left off? Now, our bucket, is that secure? Do we use security best practices? Not really. If we look at how we secure our S3 buckets properly, we need to always block public access. This is the first line of defense. And in production environments, we should enable access logging to separate buckets. This gives us that audit trail. And for encryption, we should use either S3 managed keys or customer managed keys. And finally, enforce SSL communication for all bucket interaction. And this is how we implement those security best practices using CDK. We're enabling encryption by default, we're blocking public access, we're enforcing SSL-only access. So let's talk quickly about governance as well. Use tools like AWS Config, Control Tower, and Organization SCPs to enforce compliance and security policies across your accounts. And make sure to implement proper tagging. Mark your stacks with service, microservice, and team tags. And before deployment, run security scans using tools like CDK NAG, CFN Lint, and you can also use Amazon Q Developer to review your code base for different security vulnerabilities and also code quality issues. And these are practices that help maintain control and visibility as your application grows. So looking at our diagram now, we can see how our simple 3-component service have evolved into something much more complex. We've added things for resilience, we have access logging in place, but is this more complex? It is, but each of these components, they serve a very specific purpose in making this a production-ready service. So we've covered these 5 topics to talk about how to make an application service ready. And this is one service, though. In reality, most organizations are dealing with hundreds or thousands of services. So now we need to replicate this across the organization. And there are 2 key approaches to this. One is using service blueprints, where we have reusable templates that embed all the production-ready practices that we've talked about. And the second is using architectural patterns, proven solutions to common challenges that teams can then easily adapt. And if we look at serverless service blueprints, think of these as GitHub template repositories containing a minimal but production-ready serverless service. And these serve as an excellent starting point for new projects, significantly reducing the cognitive load on your developers so they can be pre-configured with all of the best practices that we have talked about. And architectural patterns, well, these are reusable black boxes that are encapsulating these best practices. And they are building blocks that help empower your builders, but also your governance and security teams. And you can find these in a bunch of different places: AWS CDK constructs, Terraform templates, or serverlesslam.com or serverless.tf.
So that's how you make your serverless architecture production ready. For the last bit of this talk, we're going to zoom in a little bit more and look at just some practices to make your Lambda functions production ready. And Lambda, of course, is at the core of many of our architectures. In terms of how you organize your code, I like to keep my business logic separate from my infrastructure as code, so I tend to put them in their own folder, and I also like to put my tests in their own folder as well. And then for all of my infrastructure as code, things like CDK and Terraform and so on, I like to put them in a separate folder. This is different from the default template you get from CDK, where you have a bin and a lib folder, where everything gets shuffled into the lib folder, which I find really confusing. Like, which bit of code is used at runtime, which bit of code is used by CDK itself. So I like to have a bit of separation so that things are clear, like what's doing what. And also, same thing applies to your actual Lambda handler code itself. Don't just lump everything into the handler, having some separation, some structure to your code. And so that way, your handler code will just be doing things like input validation, initializing some variables, globals, and so on, before you pass the input into a logic layer. And of course, separate the logic layer from your, say, data assets layer, so that again, having that separation, that modularity, helps you make your code more testable and more portable as well, in case you ever need to move the workload from Lambda to Fargate later. And of course, you should leverage the Lambda Power Tools, which I've talked about quite a few times now, because it provides some really useful, reusable patterns for doing things like input validation, for doing batch processing, idempotency, fetching and caching parameters and secrets, but also to help you do observability as well, as we saw earlier.
And 3 key ways to improve Lambda performance: increase memory, that gives you more CPU, like we talked about before, but also network bandwidth. Consider switching to Graviton. These are ARM-based processors. It gives you 34% better price performance versus x86. And use Lambda Power Tuning to find the perfect balance between cost and performance. Lambda Power Tuning, it's an open source tool that helps you then find that optimal balance between the use of memory and to find that cost performance. It will test your Lambda functions using step functions and then give you results based on that. And then an often overlooked performance boost: just upgrading your runtime. This graph shows performance improvements from Python 3.10 to 3.13. So just look at what runtimes you're using and switch if possible. So looking ahead at serverless, we're investing in 4 key areas. We're embedding well-architected fundamentals into services. We are doing as much as we can to improve developer experience with updates like the new Lambda console editor, for instance. We're providing more and better service controls, and we're also going to expand the integration. So stay tuned for a lot more serverless goodness.
And as promised, we have given you a lot of information in the last 45 minutes, but there's still way more that we can't share. So there's a link there with more resources. Go and learn and find out more about how to build production-ready serverless applications.
And we mentioned it briefly before, serverlesslam.com, that is your go-to place to find more serverless information and to learn more about serverless. serverlesslam.com. And of course, if you want to learn even more, you should check out skillbuilder.aws as well. And with that, like Jan said, we were going to cover a lot, and we have covered a lot in 48 minutes. Thank you all very much for staying with us. I hope you enjoyed this, and thank you so much.
Thank you very much. Okay, bye-bye.